So, good afternoon, everybody. I'm Marco Valtorta. I'm chairing the proposal and comprehensive exam committee for Mr. Khandelwal. And so we first have a presentation by the candidate. I imagine 40 minutes or so. Is that what you have?
45, 50 minutes.
45, 50 minutes. We got the slides and the document. Thank you for providing the slides too. I would suggest that during the presentation, we all have questions of detail and leave major questions for the end. At the end, there will be a time for everybody to ask questions, including the audience, and we have several people in the room. And then you will meet with the committee alone, and then the committee will deliberate with you outside the room and give you their decision. Okay, so please start.
Good evening, everyone, and thank you for being here for my PhD proposal defense. I'm Vedant Khandelwal, and today I'll be presenting my PhD proposal on neurosymbolic methods for retrieval, reasoning, and planning. My committee members are Dr. Ramesh Sheth, my advisor, committee chair, Dr. Marco Valtorta, and Dr. Biplav Srivastava, Dr. Vignesh Narayan, Dr. Lior Horesh, and Dr. Francesca Rossi. So, as my title says, neurosymbolic methods for retrieval, reasoning, and planning. Why do we essentially need neurosymbolic methods? So let's go back and look at the history for a bit. From 1950 to 1990, there was symbolic era, where we coined the term artificial intelligence in 1956. We had expert system like Mycin, which could do medical diagnosis, and it was completely based on hand-coded rules and knowledge that was built by humans. And then we have in 1997 Deep Blue, which could defeat the world for the very first time a chess grandmaster by just doing brute force search on the vast state space of chess. But they hit a roadblock. What was the roadblock? There was only so much rules, so much information that could be encoded. They could not handle noise. They could not scale very well. And then came the era of neural network, specifically the revolution of deep learning. In 2012, we saw the revolution of deep learning, where we saw LXNet, which performed extremely well and was able to classify images into hundreds of classes and had exceptional performance on ImageNet data. Then in 2016, we saw AlphaGo, which used deep reinforcement learning and Monte Carlo tree search to defeat the world's Go champion. And that was totally by understanding and learning the game by playing itself. There was no human data that was provided. And then in 2020, we got the transformer architecture. And from 2022 onwards, we have several of these large language model or reasoning model that are coming up that can handle various broad varieties of these data. But while this neural network can just directly learn from data and does not need any human involvement, what was it that we missed while we gain this ability to handle noise, ability to just directly learn from data? We miss the guarantees that symbolic AI provided us. We missed the domain knowledge that was already encoded in symbolic AI and tried to learn everything. So yes, neural network and specifically modern AI like large language model or deep neural networks work very well on several tasks. Like large language models like ChatGPT was able to pass medical licensing exam, it write functional code, it almost write human-like text. There are deep neural networks that is like AlphaFold that is able to predict protein structure, classify images, generate images, speech recognition, or there are other deep neural networks which are able to solve puzzles like Rubik's Cube, which has state space of 10 to the power 19 in a very quick time and provide near optimal solution, which is not very simple. And there are other works which can learn through supervised data, generalizable heuristic. So yes, I'm not saying that neural network doesn't work, because yes, they work on several of these tasks. But the question is, when is that need when data alone stops being sufficient, and when we need to augment these neural networks with symbolic structures. So there are several challenges of these neural networks. Some of these challenges are what I've listed here. Then let's consider challenge number one, where domain knowledge is sparse. So let's consider when our training data does not encode the relationships, uh, the properties that is already out there in medical knowledge graph. So for example, if you want to search articles for surgical wound complications, generally a neural network, or let's say for this example, let's consider an LLM, would miss out on specific terms to retrieve more relevant articles like diacecine or seroma. But what solution can be? A domain ontology that already encodes these relationships along with surgical complication. Another challenge is correctness guarantees are needed. So many times the outputs must satisfy constraint, but what neural network does, and again, let's consider LLMs. LLMs produce an output which it thinks is correct, but is it correct? It's many times it's not. So for an example, let's consider LLM was given a task to generate a code. It generated a code which it thought is correct, but it does not compile. What do we need? We can potentially use like a polynomial time verifier that teaches or tells it specifically what are the errors and catches those errors. Another Another challenge here is training data lacks diversity. So one of the things on any deep neural network see is you need more and more data. If the training data is not enough, if the training data is not good, it's not diverse enough, even though you have a large training data, but it's not diverse enough, it's just going to overfit. So a quick example is consider a learned heuristic that is trained on limited IPC domains, but it fails to generalize to unseen domains. What is the solution? We can do a control domain generator to create diverse domains, and then those diverse domains can be used to learn a better heuristic. So I want to map these challenges that I mentioned to the cognitive pipeline of any intelligent system. Any intelligent system, first given a problem, it retrieves, access relevant knowledge, it reasons, draws valid conclusion on that knowledge, it plans, it selects action towards their goals. Just a quick example here. Uh, the problem is robot is fulfilling customer orders. So to retrieve, it queries inventory database for item locations, shelf position, product details. What is the challenge? If you're using an embedding based method, there is a chance that it can miss those spatial relationships, like item is in aisle 3, bin 2 is near aisle 3, or bin 5 is near aisle 3. Reason on that data, determine which requested item are actually in stock from the inventory data, infer correct item, whether what was the size, what was the model, what was the weight based on product metadata. Challenge, maybe if you use an LLM, it incorrectly classifies, it probably classifies a much less weighted product as the right product that needs to be identified or needs to be given to fulfill the order. Plan, select action towards goal. Finding a sequence of actions to navigate all the every single packet station and connect all the packets. Here, maybe a heuristic that is trained on limited data fails to generalize to more number of packages, more number of packet stations. So then what is a potential solution? Neurosymbolic, where I'm not saying that neural network doesn't work or we have to replace neural. The whole idea is we have to augment neural network with symbolic structure, where neural network can learn from data, can handle noise, can scale well, and symbolic encodes domain knowledge or ontology. It provides guarantees. Just a quick example of how this can work in the 3 stages. For retrieval, we can use domain-specific ontologies like mesh, UMLS, control lexicons, or warehouse ontology in the case of previous example. For reasoning, we can use simple verifiers, very polynomial time verifiers, which can identify and with the guarantee say, yes, your solution is correct, or no, your solution is incorrect. And for planning, we can have a domain generator that generates data through a controlled mechanism and gives us driver set of training data, which then can be used to learn a more generalizable heuristic. That brings to my research questions that I'll be addressing. Research question 1 is, how can these domain ontologies and controlled lexicons improve neural retrieval in knowledge intensive domains. So again, retrieve or retrieval field is much big. My scope for this particular work is limited problems where these retrieval tasks have knowledge and can be grounded into existing knowledge or ontologies. Examples are medical systematic reviews or obtaining mental health labels for surveillance on social media data. Reason, the research question 2 says, how can these polynomial time verifiers provide targeted feedback to guide neural iterative correction? Here, again, the reasoning has a lot of different, it's a huge field. My scope is limited to any reasoning task that has a polynomial time verifier that, that does not require it to solve the problem completely. And then research question 3 asks, how can control data generation enable heuristics to generalize across domains? And here planning again includes pathfinding problems, scheduling problem, optimization problem. My scope is limited to pathfinding problems like N-puzzle, Bloxwell, and Rubik's Cube. That brings to my dissertation proposal statement. Says, neural network achieve remarkable results but benefit from symbolic augmentation when domain knowledge is sparse, correctness guarantees are needed, or training data lacks diversity. This dissertation demonstrates that augmenting neural networks with symbolic structure improves retrieval precision, enable reasoning self-correction through verification feedback, and helps learn generalizable heuristic for planning through controlled data generation. And here is the outline for my presentation today. I'll first go over the completed works. And here are some of the select publication for each of the research questions. And then I'll talk about the proposed work, which integrates and shows application of the already done work into different fields. Research question 1. How can domain ontologies and controlled lexicon improve neural retrieval in knowledge intensive domain? So here I have two works. One is domain agnostic neurosymbolic approach for big social data analysis, where I retrieve relevant mental health labels for social media data. And another work is systematic reviews. Given the time constraint for today, I'll be discussing about the systematic reviews work only. So let's understand what exactly is systematic reviews. Systematic reviews are the gold standard of evidence-based medicine. These are the reviews. These are the works that are very much relevant and for policymakers, for new advancement in medicines that are going out, but they are very time-consuming and error-prone. One of the research articles says that research has repeatedly shown that systematic review searches contains error that impact precision and recall, and which can impact the quality of reviews conclusions. So let's really understand what exactly is this problem of systematic review. These systematic reviews are done generally with the help of librarians, where for every single query of a systematic review, they take 8 to 15 hours per review alone for query development. Once they do develop this query, they have to manually construct and add control vocabulary to this query, which is very time intensive. And then they have to screen through thousands of articles to identify the relevant articles. And that is when they finish first run of identifying initial set of relevant articles for a given query. There have been, with limited human expert resources, there have been a 26% annual growth in this systematic review publications. One challenge that will be more focusing on addressing in this today is, let's consider a query, surgical wound complication. Our initial query that is written says surgical wound, mesh term, or wound infection, and some other terms. But what this particular query is missing out is some other term that is very much relevant to surgical wound complication. It's already encoded in existing knowledge graph, but it's not yet there in this query. Is dehiscence, seroma, hematoma, and surgical site infections. These terms, as I said, exist in mesh terminology, but are very time consuming to identify and add it. So why don't we use LLMs? LLMs have been shown to work really well, handle these tasks, but LLM or LLM-based tools like Cite, Consensus, Perplexity, they help with natural language queries, but they miss out on the critical requirements that is required for any systematic review. What are those requirements? Reproducibility. Every single time the same query, when a same query is given, it should produce same result. LLMs outputs varies between runs, so it cannot be used. Interpretability. Reviewers must document exact search strategy. It should show how the query was created, what mesh terminology was used. It should be reproducible by the tip of the final query. LLMs cannot show a structured query or cannot show what was the exact strategy they did to retrieve those articles. Control vocabulary. Use standard terms in mesh and UMLS so that every single time if somebody is doing a particular systematic review on a specific disease, it uses these terms to make sure it is tied to the same set of disease family and it's not creating something new. And these requirements, I'm not making it up, it's required by coherence guidelines. This is the guidelines that the systematic reviewers are supposed to use. LM's limitation, as I mentioned here, they don't really have access to control vocabulary. Maybe we can do RAG. They cannot generate database compatible queries, not reliably at least, and they hallucinate citations, and results are not reproducible. So LLMs excel at the natural language understanding, but it lacks the domain knowledge, the structure that is needed, and these critical requirements that is needed to solve this problem. So then for that, we propose NeuroLit Navigator. This is our approach, a neurosymbolic approach to solve this problem. Let's see how this works. Given an input query, here in this case is antimicrobial agents and suture techniques on prevention of surgical site infections, and along with that sentinel articles, we extract seed concepts. Seed concepts are the important concepts from each query. Once we have extracted those concepts, which are here, we pass it through two different steps. One is vocabulary extension to extend or expand these set of terms by grounding it in and identifying more relevant terms in knowledge graphs like mesh hierarchy. And we do query expansion. We use masked language models by masking each of the relevant concepts within the query and pass it through the MLM to identify and get the terms which it has seen are contextually relevant in its training data. Once we have the expanded query and concepts and the extended vocabulary, we get a new set of terms. That, along with the concepts, is given to PubMed query formulation. A quick view of how that PubMed query looks like is something like this, where we have these mesh terms. Mesh terms are again the control vocabularies which are out there specifically obtained from the knowledge graph. And then we have several other terms which are TIAP to check if any of these terms matched of any of the articles title or abstract. Once we have a set of articles retrieved, we send it, we do another step of retrieval and re-ranking where we get those articles, we re-rank those based on its similarity to the given input query and sentinel articles, and then the final set of articles is given as output. One thing to notice here, it's not a complete system. We finish here. That means this entire system currently just solves the problem of first run, the initial set of retrieved relevant articles. Now let's look at a bit more detail how exactly is this query expansion and vocabulary extension is working. So once we get, as I mentioned, user input query, we extract seed concepts, and then we have two complementary extensions working in parallel. One is knowledge graph. We take the specific concepts and we do two-hop traversal through mesh terms and UMLS, where we identify the relevant terms. These becomes a candidate set of terms, and knowledge graph is used to provide the hierarchical relationships. Then on the other hand, we do masked LM. Here we use clinical bird, where we mask the specific concepts that are identified and pass it through the MLM, where then MLM tries to predict what might be the word here. These words are give us new sets of terms which are being used in the same context in the data that has seen during training. Once we have these two sets of candidate new terms, we filter the new terms by making sure that every single additional term that we are adding is relevant. And we perform semantics filtering by filtering out the terms which has a similarity of less than 0.7. And then the final set of terms are our expanded query terms. Then once we have the expanded query terms, that along with the concepts goes into query formulation. In the query formulation, we perform something we call as iterative query refinement. What exactly it is? So let's look at this quick example. Given this query, what we do is we identify these entities, 4 entities. So for first iteration, what we do is we use all the entities, generate a PubMed SQL query, and we are only able to retrieve 12 articles, which is less than the minimum number of articles that we want to retrieve. So then to handle this issue, what we identify is this particular query, the query for first iteration, is too specific. It has too many constraints. So what we do is we take the concept that is least relevant to the input query and we remove it from the query. So now what we have is a more general query that can then retrieve more articles, and then we can go to our next step. So this not only makes sure that you get some articles, if at all you're not getting any articles, but you also get articles through concepts which are most relevant. And this is the algorithm for it. Here essentially what we do is every single time we start off with the most specific query with the most constraint, and we keep on removing constraints as in terms of the concepts which are least relevant, and we end up with a final query that is most general specific query. Then a quick experiment that we ran to show how relevant is this iterative query refinement process is here. So we ran 20 different queries, and for the round one, where we were just always using the initial query, there was no query refinement. The relevance of the retrieved articles that was retrieved was 28%. And in the round two, when we were using these iterative query refinement, we got an improvement, and then the relevance was 65%. Yes, we did increase time, but there was a significant increase in the relevance as well as the improvement in query. Then here, what we do is we also wanted to compare how well does our work fall against existing LLM-based tools like Scite, Consensus, Perplexity. So we ran our first experiment that was on public health queries. We had 12 academic librarians who evaluated the top 5 results from each system output for 20 queries. And they evaluated in terms of whether a particular article that was retrieved was relevant or not relevant. And what we see is, and the Cohen's-Kappa score was 0.76, the agreement score of the evaluators. And what we see here is that consensus achieves the best relevance percentage, but it does not really have any of the reproducibility, interpretability, or use of control vocabulary, whereas NeuroLit achieves 36% relevance and has all the 3 requirements ticked off. These results, the results are based on the queries that was done with these LLM-based tools as of March 2024. Then we also wanted to see if this particular work can be extended to computer science queries. And for that, we use 4 student evaluators rating top 3 results from each system output for 20 queries. We had a Cohen's kappa of 0.62. And here we clearly see that we achieve a relevance percentage of 65% with all the 3 reproducibility, interpretability, and use of control vocabulary checked. These results were as of April 2025. So what we achieved here is not only relevance, not only not only get all the 3 reproducibility, interpretability, and control vocabulary requirements, but we also reduced the time by 90%. And then this tool was deployed across 12 universities in US for public health queries. So takeaway for this is we clearly see that control vocabularies outperforms and help outperform LLM-based system. We can clearly see Neurosymbolic is complementing, it's not competing with each other. We use KZ expansion, we use MLMs to provide more new terms, and together we get a more comprehensive set of terms. And one of the things that to note is this particular system requires domain specific knowledge, database, and embedding model. Like for public health query, we use mesh terms as knowledge base, PubMed database, and clinical bird. While for computer science query, we use semantic scholar database, Cybert, LLM, and DBpedia as our knowledge. So now neurosymbolic approach improves what we retrieve. But what about reasoning over that content? So even with grounded retrieval, the system can still produce incorrect outputs. That is what we handle in RQ2. RQ2 says the question of RQ2 is how can polynomial time verifiers provide targeted feedback to guide neural iterative self-correction? And here, uh, this neural is very specific to LLM. We look at how LLM can be used and we perform iterations with LLM to improve their output over the time. Again, I have two works in this for this RQ, but I'll be focusing on only the second one. So yes, again, LLM is fast. LLM has been shown to generalize and adapt to several different tasks, and it can do well, but it struggles with correctness. It struggles with when the constraints are harder, when you have long instruction following tasks. A quick example is, again, LLM is given color the vertices, so no adjacent vertices share a color. This is the graph. It produces an output that it thinks is correct, but it is not actually correct. The C and D are adjacent and are still same color. On the other hand, sorry, B and A and D are adjacent. Sorry for that. And then we have for code debugging, we have a task where we ask it to fix a bug in the particular code. It does, and the code compiles, but it fails all the test cases. That means it did not really solve the bug as to solve the and get the final correct output. So it failed test cases. So LM struggles, it's approximate, it's probabilistic. There is no backtracking capability for it to go back and say, oh no, there is a violation of the constraints, and then it can change the output. There are reasoning models that can handle a much harder constraint problem, but they are expensive in terms of time and compute. And there are also symbolic solvers, but they are really, really slow. So here, a potential opportunity is we can use the verification, a verifier that is fast, polynomial time, complexity, errors, which can identify errors precisely, convert it into targeted feedback, and then we use this feedback to guide self-connection. And we use a combination of these powerful and slow models and fast and less powerful models to solve the trade-off in time and success rate. So for that, we propose SOFAI architecture with metacognition. SOFAI architecture is a cognitive architecture that is inspired by Daniel Kahneman's theory of thinking fast and slow. This architecture that we see here builds on the original SOFAI architecture, which did not have any loop with an S1 solver. It used to take the problem S1 solver. If it solved the problem, then it gives as an output. If it did not, it used to fall back in S2 solver. Here, in this case, what we do is we have a fast S1 solver. In this case, would be LLM, and a slow S2 solver. On given an input problem instance to S1 solver, it provides a candidate solution, which is then given to solution verifier, verify. If the solution is correct, that's given as output. If it's not correct, it goes into a iterative metacognitive loop with the LLM, which is a S1 solver. It identifies the issues, it identifies the errors, it converts it into targeted feedback, and that targeted feedback is given back to S1 solver. This particular step is done until it reaches a duration limit that is predefined, or it does not show any improvement over 2 iterations. So let's say over the 2 improvement, it's making the same error. The metacognition says, maybe it's not worth it doing this. It's not improving. And then it falls back on S2 solver, which again gives a solution. And if the solution is correct, it's given as output. Once a problem is solved, that is stored in episodic memory. Episodic memory is like experience memory that stores the input problem instance and solution, and it's further retrieved later on for adding relevant context to the S1 solver. Here in the later slides, we'll talk about 2 instances of SOFAI. SOFAI v2, where S1 is instantiated with an LLM, S2 is instantiated with a symbolic solver, and SOFAI LM, where S1 is LLM and S2 is LRM. For this work, we evaluate our architecture on 2 domains. One is graph coloring decision problem. where we have input graph and a fixed number of color k, and either we output a coloring assignment g if it's possible, or say that the problem is not solvable. For this work, we produce graph of different vertexes, five ranging to 50, and different edge probability 0.1 to 0.9. Each of the pair of graph size and edge probability generate 100 problems, and it's stored in Dmax format. A quick example is right here. I hope that's visible. We create different problem configuration that we test later on. For graph coloring decision problem, one is all solvable, M100, 0, M50, is solvable and unsolvable. And then we have 0, 100, where it's all unsolvable problems. And these unsolvable problems are produced by giving a K, which is less than chromatic number. And chromatic number for any graph is the minimum number of color that you require to give a coloring assignment for that graph. The other domain is code debugging, debug bench. This particular benchmark was created by, it's an existing benchmark that was created by taking the lead code problems, its correct solution, and then injecting one particular bug anywhere in that correct solution, making that a buggy code. The benchmark has about 4,000 problems of Python and C++ language, and each instance has one single bug. And the whole idea, the verifier that we use is lead code API that outputs either if there is a compilation error, if there is a failed test case, and the expected output, what was the input and the code output, and if it was a complete success. So now let's see for SOFAI V2 and for graph coloring decision problem, how does our architecture work? So here, as I mentioned, we have S1 as LLM Mistral 7B model, and S2 as degree of saturation with backtracking, which is a complete symbolic solver. Here, SOFAI V1 refers to the initial SOFAI architecture, which does not have any looping. So it's either provide solution with S1 or S2. We have S2 means S2 only. SOFAI V2 refers to the architecture that we just saw, and S1 refers to S1 only. So just one single run with one single pass with S1. Here we run two experiments. First experiments is done with a 200-second time limit per instance. And here the results that we see is with edge probability 0.5. So here, what we wanted to compare is the success rate percentage for each of these different solvers across these different graph size. And what we see that SOFAI V2 performs the best across all. It is performing the best in all solvable cases, in all unsolvable cases, and in mixed domains. While, and there are also instances where S2 does not solve any problems, but SOFAI V2 does solve those problems. So when we saw that, yes, SOFAI V2 is performing well, we wanted to really understand, is it also doing good on time? So then what we did is we ran another experiment that is done without time limit. And this is, again, we have results for graphs generated with edge probability 0.5. And here what we see clearly is as you increase the graph size, SOFAI V2 significantly becomes, it starts showing that it's faster significantly. And we even see 30% speed up against SOFAI V1 and S2 for unsolvable and mixed problem set here. So one thing that we can clearly see is then when there is a time limit, it solves more problem. When there is no time limit, it solves the problem faster. How it's able to do that? Because it's not always calling the S2 solver, the symbolic solver. It is able to perform these feedback iterative metacognitive loop with S1 solver to improve its solution and maybe even get a final correct solution without even invoking S2. So it's only invoking S2 when needed. Then we wanted to really see how does these different feedbacks really affect or improves the output of LLM. So here in this case, and from this slide onwards, we'll be looking at SOFAI LM results, where S1 is an LLM, Granite 3.38 billion without thinking, and S2 is an LRM, a thinking model, DeepSeek R1 8 billion. So just to briefly give an idea, how does this entire input output, this iterative loop looks like, here is a quick input problem prompt for code debugging domain. Once this problem prompt is given as input, LLM generates. This is the first attempt of LLM generating an finally corrected code, which is tested against lead code API, and lead code API says, oh no, the code is not completely correct. And then this is the feedback that we provide. Code failed, failing test case, expected output, our code's output. LLM's codes output, and the LLM does another attempt and generates correct solution. So this is how iterative feedback looks like. Now, coming back to results, what we have here is we have results on two domains: graph coloring for graph of size 25 and all solvable graphs, and we have for code debugging for Python and C++. Here in this in this graph, what we see is y-axis is success rate, x-axis is time taken, and the different points here represents different solvers. So one is LLM only, LRM only. We have LLM at 5, at 10, at 15. So LLM at K means LLM with up to K iterations with metacognition. So LLM at 5 means you do up to 5 iterations, at 10 means up to 10, at 15 means up to 15 iterations. Here, as we can clearly see, the LLM at 15 performs way better compared to LRM or LLM only, and takes much less time to solve the problem in graph coloring. Similarly, for code debugging, we see it's the same case. While LLM at 15 solves a lot more problem, it takes more time than LRM, whereas LLM at 10 still takes less time, but still solves a lot more problem. So then, yes, iterative feedback does improve LLM's output. We clearly see that here. Then we wanted to see how does these feedback, these memory types that we have, how can we change it, or does changing it really affect the performance? So here in this case, what we do is we test 4 different configuration of feedback and episodic memory type for graph coloring decision problem for node of size 25. And we have these 2 types of feedback: single line feedback that stores the same information as one line, multi-line feedback, same information, but in a more structured format. And then we have minimal episodic memory that I just mentioned, that episodic memory stores problem instance and solution, and extended episodic memory that along with this stores the history of iteration with S1 solver. On seeing these different configuration, what we see is multi-line feedback outperforms single line feedback by a margin, by huge margin actually, and minimal episodic memory performs better than extended episodic memory. So at the end, our best configuration is multi-line feedback with minimal episodic memory. And history with LLM does not prove to be useful here. Then we wanted to see how can we improve the synergy of S1 metacognition with S2, in this case, which is an LRM. So here what we do is we try 3 different prompting strategies with LRM. One is problem only, where LRM, as usual, will get the problem as input when the metacognition fallbacks on it. Best attempt, where LRM along with the problem gets the best attempt that was made with LLM and metacognitive loop. And full history, LRM gets problem in all attempts plus feedback with S1, which is our LLM. And here what we see is a very contrasting results. For graph coloring, we see that problem instance only SOFAI seems to be performing the best, whereas for code debugging, problem instance only performs the worst, whereas full history performs the best. And here what we realize is that for graph coloring problem, any of the candidate solution, the incorrect partial solution that are produced by S1 is not really relevant. Why? Because even though those partial set of coloring might be correct, those might not be present in the final.
I have a very quick question of detail.
Yes.
And it's really naive. What does the acronym LRM stand for?
Large reasoning model.
Thank you. I don't see it defined in your document. That's why I asked. I may have missed it, but I didn't see it.
Sorry for that.
Thank you.
And right. So what we see is that those partial solutions, even though those partial coloring might be correct, they might not be a part of the actual final correct coloring for graph coloring. Whereas in case of code debugging, we know that the correction we have to make is local. We know that there is only one single line or a part of the code that is buggy, rest all the code is correct. So that's why we see that in this case of code debugging, this history of trying out different things and failing does help the final LRM, whereas in case of graph coloring, it does not. It just acts as a noise. So then what are the takeaways for this? We saw that targeted feedbacks enables LLM self-correction without any fine-tuning. Fast verification is the key to doing the self-verification. Architecture this architecture can be generalized to different solver types. We saw S2 where S2 was an LRM, a reasoning model, and we also saw instantiation where S2 was a symbolic solver. And domain structure, as we saw in the last slide, domain structure determines what information might be good for a particular problem to be shared to S2 or the LRM. And this particular architecture can generalize to any reasoning task with polynomial time verifier. So it just requires domain specific verifier and feedback generator for any of the new tasks. So now we saw that verification guides reasoning when we have those domain specific fast verifier. But what about domains where we need heuristic to identify a sequence of action? How can a neural network effectively generalize across these different domains? That's what we address in RQ3. RQ3 asks, how can control data generation enable learned heuristic to generalize across domain? Here again, I have 3 papers, but given the time, I'll be talking about PDDL Fuse and DeepCube AF. So planning problem, again, as I mentioned earlier, has a lot of different problems. It has pathfinding problem, scheduling problem, optimization problem. Here in our case, we'll be only focusing on pathfinding problems. So a pathfinding problem is where you have a start state, you have a goal state, and you want to find a sequence of action that takes you from start state to goal state. Pathfinding problem domains span multiple disciplines. It goes from robotics to quantum computing, and it influences diverse problem solving like puzzle solving and robot path planning.
If you go one slide back, please. Thank you.
Some of the existing work which solve these pathfinding problems are DeepCube that learns domain-specific heuristic via deep reinforcement learning. One of the drawbacks for that is any small change, the DeepCube would have to be retrained from scratch, and that is an expensive training. We have Goose that learns generalizable heuristic via supervised learning, but generating supervised learning data for pathfinding problems is expensive. So only limited data, training data, and narrow domain or narrow training data leads to poor generalization. We also have LLMs, as we have discussed in the other 2 RQs. LLMs are said to be zero-shot reasoners across different tasks, but they don't really work well for planning. They hallucinate invalid actions. They can't verify whether their plan is correct, and they fail really bad on long horizon tasks. So a desired solution is a foundation heuristic that is trained on diverse enough data. It's trained in an unsupervised manner and still able to generalize to new unseen domains with minimal or maybe no fine tuning at all. So for that, we first tackle a challenge of generating diverse data. So we introduce PDDL Fuse. This is a symbolic domain generator that fuses or combines existing domains to create new diverse domains based on a set of parameters. Those parameters are adding or deleting a precondition from an action, adding or deleting an effect from an action, negating a predicate that is being added to precondition or effect, and the number of objects for the problem. These parameters, as I just mentioned, can be tweaked to control the difficulty of a generated domain. Just a quick example of the generated domain is right here. This domain is generated by fusing blocks world and gripper domain. So we have one action that is from blocks world. We have another action that is from gripper. And these preconditions have both predicates from gripper as well as blocks world. So why do we actually do that? Why do we want to take existing domains, randomize it, some sort of parameter tweaking and generate new domains? Domain randomization is a process that has been shown to work in reinforcement learning in case of robotics. And the whole idea was, how can we bring in what has already worked in reinforcement learning for robotics to pathfinding planning problems here? So a quick, I'll quickly go over the algorithm. So it takes in 2 base domains. For each of the actions in base domains, it first decides whether it wants to keep that action in the new generated domain. If it does, then it at a given probability parameter of adding a precondition, adds new precondition. given a probability, it's add effects, remove precondition, remove effects, and whatever precondition or effects have a new predicate added, based on a probability, it negates those. And then it generates a completely new domain. So then we wanted to really see if these domains generated are really relevant. Can we make it harder? Can it even be solved by existing planners to make sense? So here for this experiment, what we do is we generate several domains by taking Gripper and Bloxworld as the base domain for all the experiments and results that you see in this slide. And we generate domains of varying difficulty. Just going over the heat map, we vary the probability of adding precondition effect or probability removing precondition effect and negation probability by 0.3, 0.5, or 0.7. And as we see here that as we test fast downward, fast forward, fast downward planner with fast forward heuristic, we see as we go from left to right, we clearly see the color of the heat map fading. That means lower the color, less number of problems it solved, darker the color, more problems it solved. So we really could see that as we are tweaking these parameters, we are able to generate more and more diverse and complex domains that even existing planners, and given a time limit here for this experiment, there was a 200-second time limit, given a time limit cannot solve. Then we also wanted to see what happens when we do a do this generation over subsequent depths. So what do I mean by that? If a particular depth 0 means you have the original base domains, depth 1 means you have the generated domains using the base set of domains, and any subsequent levels of depth means that you are considering the generated domains on the previous depth as part of the base domain that you use to that you combine and generate new domains. So here what we do is we test for depth 0 to 5 for 10 problems per depth, and we test here two planners. One is fast downward planner with fast forward heuristic, LPG, and then we also test Goose, which is the supervised learning based heuristic, and we also train a our model value, our RL model, which is based on approximate value iteration on the generated domains, PDDL fuse generated domains. And what we essentially see is that these two planners that we see here perform really well on initial depths, but as the depth starts increasing, they start deteriorating. Whereas Boost starts deteriorating the fastest, then LPG, and then our AVI based model. So from this, what we understand, we can tweak, we can generate diverse domains, we can control these parameters to not only generate diverse domains, but domains with varying difficulty. So then now, once we have the issue of data figured out, how do we really train a model that can generalize across these different domains? So for that, we present DeepCube AF, learning generalizable heuristic. DeepCube AF, it takes and it generates and takes a training data using PDDL fuse, but it generates diverse domains and problems. Those domain and problem is given to HER model that generates more training data from the same problem and domain for the model to be trained on. Once we have more in HER is hindsight experience replay. More data generated, we convert all the data into graph representation. Here, the graph representation that we use is SLG strips learning graph representation. This is an existing representation from a different paper, which has shown to perform really good in terms of encoding graphs and generalizing across domain. So it encodes the domain's action, predicates, and the initial state and goal state. A quick example of how it encodes a particular action is here an action A for predicates P0 to P4. The black edges represents the precondition for that action. Blue edges represents the effects for that action. And the red edges shows the delete effect. That means once the action is taken, those two predicates will cease to be true. Now, why do this? And then we use that graph represented training data and give it to GNN and learn our generalizable heuristic. But why does this actually work? It works for two major reasons. First, PDL fuse, it is able to generate diverse data. So now model not only sees, it doesn't see a limited set of narrow domains, it sees a lot more diverse set of domains. And the second is hindsight experience replay. So in this case of learning in an unsupervised manner where we do not have a solution label, we face a problem of sparse reward. That means the model only gets a proper definite reward, or it really learns better when it actually reaches a goal. But given these domains are being generated are very diverse, problems being generated are very diverse, it clearly creates a problem of sparse domains. So then what is the use of hindsight experience replay? What it does is, given a particular start state and goal state, it will identify a trajectory, but just taking random step from start state trying to reach goal state. Then what hindsight experience replay says is, okay, you did not reach goal state, that is fine. It doesn't mean that this data, this exploration that you did is completely useless. It stores those middle states where it reached, which is not goal state, and now creates this new pairs of start state and goal state, which are different from the initial start state and goal state pair that was there in the problem domain. And this not only adds, oh, this not only adds more training data, but it essentially also gives a chance to get quicker rewards. Okay, so in results, we wanted to we here particularly check the generalization on 3 domains. Just to be clear, the model never actually sees blocks world, NPuzzle, or spanner, the originals, these of domains. Why? Because it's only trained on PDDL fuse generated domains, which never actually produces the original domains. So we check on Bloxwell 90 problems, NPuzzle 50 problems, and Spanner 90 problems. And for each of these, for Bloxwell, we have blocks ranging from 15 to 100, NPuzzle ranging from 5 to 9, and Spanner ranging from 15 spanners and nuts ranging from 15 to 100. Here we perform this experiment with a time limit of 600 seconds, and the search algorithm that we use for our model is batch weighted A star search. Key findings, as we can clearly see, that for Bloxwell, fast run and fast forward solves 74%, while our model solves more problems. For NPuzzle, our model solves more problems, while it's slow. But clearly, to actually see in Spanner, with this given 600-second time limit, neither goose nor fast downward with fast forward heuristic solves any problem, whereas our model solves 11% of the problem. So we can clearly see that this period fuse generated domains are enabling generalization. There is a transfer capability in the model that we train. Takeaway, symbolic domain generation enables generalization. Domain randomization we transferred the idea of domain randomization from sim to real in robotics to planning, domain to domain. And graph representation that we use does preserve the domain structure and is able to then generalize to larger and different domains. And yes, fine version heuristics are achievable. So then RQ1, we saw that knowledge graphs, encoding or grounding retrieval in knowledge graphs provide better retrieval. Fast verifiers guides reasoning and improve the results. We have symbolic domain generation, give generalizable heuristic for planning. So in all 3, symbolic augments neural network to give a better system. Quickly going over proposed work. First is using the learning from RQ1 and RQ3, want to apply into replanning problem in smart manufacturing. So in smart manufacturing case, specifically in assembly pipelines, what we essentially see is they follow very strict set of plant sequences. And once a failure occur, the current approaches to stop everything, manually handle the anomaly, the failure that occurred, that causes significant downtime. So what I'm proposing is a neurosymbolic approach for replanning in smart manufacturing, where we train a heuristic function for replanning on the fly. So it takes in the state representation of anomaly of the environment which has an anomaly, and it is able to replan and identify the next best action. And we use an ontology for explainability to really identify why a particular action was done, why that anomaly occurred, and why is it an anomaly. This is done in collaboration with Next, which has the rocket assembly pipeline, and existing works by other students, which has domain specific in ontology and anomaly prediction. So this is just to quickly show what I have right now is a simulator that I've built mimicking the assembly pipeline at the Next, which not only does the entire process as it is done at the Next, but it also does encode anomalies at random. And the final work is a complete system that, as we saw, the complete intelligence system that not only has retrieval reasoning, but also has planning. So for that, I'm going to be using asset ops benchmark. So what is asset ops benchmark? It is a benchmark that simulates the real world industrial problem, like for chillers or AHUs, and has data, the sensor data, work order data, or FMEA manuals. The task is given a particular problem scenario. The agent must be able to decide which data to query, whether it has to diagnose anomaly, execute maintenance action, or something. One of the limitations of this existing system is reliability gap. A particular agent says it has done the task, but it hasn't actually done the task. So it's not reliable, it hallucinates. An efficiency trade-off. The plan and execute, which you have a plan from the start and you're just going to execute that no matter what happens, does not work very well. But tool as an agent, which tries to replan every single second, does not, is very slow. So then to solve ambiguity, I'm going to use the knowledge grounding work from Retrieval, to solving reliability, the metacognitive governance from RQ2, and solve efficiency, the generalizable heuristic from RQ3. Timeline Jan 26th, I'll be done with the span manufacturing, writing and implementation. By Feb, I want to finish the system. And by May, I want to defend my dissertation. And here are the impacts.